I'm gonna start up an AWS cluster right now. All right. So at the end of so there's this. Actually, let me go back to slides for a second. Where did I put it? Oh, I didn't put it in here. This GitHub repository. People probably can't read that. So on my page, sparse PageRank. There's one file in there. This is an implementation of PageRank in Spark. Down at the bottom is can I get this? Come on. Never mind, I've got it in Emacs. Down at the bottom is a command to create a 5-node cluster. So 4 worker nodes, 1 head. I'm just going to use that real quick to start it up. And while that starts to spin up, we can go on. All right. Questions about the creating a cluster? Are there some? I mean, we've been using, yes?
Why are you using a 4-node cluster, a 5-node cluster there?
I recommended a 3-node cluster to start with. This will work on a 3-node cluster. It just goes faster because it's very easy to start a very large cluster. I mean, you are limited by AWS, but if I tell you to start a 10-node cluster, then if you make a mistake, it's 3 times as worse. But for problem 5, it'll work on a 3-node cluster, so 2 workers. It'll take about 2 minutes in iteration, maybe less, maybe more. Some people are up to like 20-node clusters, and there it's like it runs in about a minute overall, if everything's partitioned right. So the 3-node was just like to keep you from shooting yourself in the foot. If you really want to shoot yourself in the foot, you can take the safety off and go ahead. So I'm going to start up 5. I'm just using the MX large, whatever. So everything else is basically default, except for if you didn't see this in Piazza, it's broken across there, but they released EMR 4.1.0, which has Spark 1.5 instead of Spark 1.4, I think, or whatever was there before. So I'm going to use that. This is going to take a little while to spin up. We can go to here. And so go to my cluster list. I've got one starting up, so we'll just wait, all right? It'll start up. It'll be a few minutes, okay? And we'll just let that go while I start talking about other things. We'll come back to this. Okay, so AWS, Spark partitioning, all right. Best results we've had when actually launching the job on AWS, which we'll see in a minute, is 1 executor per worker node. That's the num executors. So in this case, I started with 5. I have 4 worker nodes, so I'm going to do 4 when we get to that. With 48 cores per executor, the virtual machines have 4 cores. A lot of the operations here are I/O bound, and so starting up more executor cores, basically this is how many Python processes are going to be running underneath. This is how many sort of workers or overviewers or overseers there are. This one is how many Python processes underneath to use, or if we were doing it in Scala, how many parallel threads to run. So 4 is a good default here. And then it's worth upping the memory with the executor memory to like 5 gigabytes. That's for like storage of serialization. You have, each of these cores has 11 gigabytes by default. So you can put it up to around 8 safely and then leave some overhead. That just will save you some crashes for if you start to blow out the serialization if you're storing a lot of things. But that's also been helpful. I think all of these defaults should be in the Piazza post that we updated these, all right? We'll see this in a bit, but just so you know. All right, let's talk about 2 things, partitioning and caching. All right, we've talked about, if you're going to join, which you're going to do because of the homework, check partitioning. I send out a simple Python function. It doesn't work in early Spark. It works in like Spark 1.2. Or it doesn't work in Spark 1.2. It works in Spark 1.5 and I think 1.4. Or you can just check that the partitions are the same on 2 things. So co-partitioned just means the same number of partitions as long as you have the same partition function. But just use the default. Just let Spark choose the partition function. Okay? And this will be fine. And there's no cost checking. We're going to show some code in just a bit. We're going to work through the PageRank algorithm in Spark. And I'm going to just add a bunch of checks. I think this RDD and this RD are co-partitioned. I'm going to assert that. So that's a Python built-in, assert, which basically says evaluate this. If it's false, die. So I'm just going to assert that the things that I think are co-partitioned are co-partitioned. And that will allow me to make sure that whenever I do a join, there's no shuffle, right? So that's the main reason you co-partition. Co-partition data RDDs, when you join them or do any pairwise RDD function, there's no shuffle. And so it's fast, okay? Yes?
So in my final when I was looking at the Spark web UI, it looked like the majority of the time after I co-partition stuff was being taken up by partition by. Is that expected? Whereas most of the sort of slow steps would be just in the repartitioning?
Partition by at which point? So partition by at the very beginning, when you first partition, there'll be a partition by call. And that can be large, right, to build up just the initial data. After that, it shouldn't be large because most of what we're working with are small data sets. There should be a lot more compute. You're talking about problem 4, problem 5? 5. Shouldn't be that much cost later for partition by because the data set is small. You may have to, it's possible that you're building things, you may be breaking the partitioning somewhere. And we'll talk about what breaks partitions. Or that's probably what's happening. If you have more you should have, if you have an expensive partition by, you probably it's probably that partitions are being broken. Partition, I didn't put a slide in this, but some things break partitioning, in the sense of Spark loses its knowledge of what's partitioned, and so it does expensive operations. Map, if you take a partitioned RDD and you run map on it to produce another RDD, that second RDD is not partitioned, even if you don't modify the key, right? All partitioned RDDs are always key value. They're partitioned by the key, by the hash of the key. If you call map or anything that does something like map that could modify the key, even if you don't, then Spark loses its knowledge of how it's partitioned and will shuffle it, even though everything's going to go exactly to the same place, okay? You can call map, if you know you're not going to modify the key, but you need access to the key value in your function, in your map function. There is an argument preserves, check me on this, preserves partitioning. What? Yeah. I'm not sure about if I'm spelling it right. All right. This says, yes, I'm taking the key and I'm producing a value, but I guarantee that this output here, some x, that x will be of the form same key, comma, something. So I'm preserving the key. And I'm preserving the partitioning that would occur if I were partitioning by this, okay? If you don't do this, if you actually do change the key, Spark it won't crash, but you'll start doing things like join with key won't actually bring, or group by key won't actually bring all your data together. It'll say, oh, well, it's partitioned. I don't need to do any shuffling. So if there is data that's someplace else with a new key, I'll just leave it there, all right? So this is useful and dangerous. A couple of people have hit bugs with this already, okay? This can only be true if you actually do preserve the key. Some of the functions you may want access to the key value in what you're going to evaluate here. And this is the way to get it while still producing a partitioned output, okay? And that basically then keeps map from breaking the partitioning. All right. the other thing I want to talk about before we start going through code, and we'll reiterate some of these as we go through, is caching, all right? So, caching, couple things. Memory is limited. Don't just start sprinkling cache in wherever, right? It doesn't help. It's only useful for things that are going to be referred to multiple times, and only if it's going to be passed to another, or it's going to be passed to another iteration. So especially if you don't put any caching in and you have an iterative chain of RDDs, what does that look like? So, you know, the BFS problem or something like that. So I have the first iteration, I have some number of RDDs in it, right? They have some relationship, they produce some other RDDs. Some of those come out, right? I might have some other, this one might just be passed to the next one. That might just be my graph, this might be distances. I do the same sort of computations, right? Everything looks the same in terms of the history here. Right, this one just comes across. Right, okay. So these are, the big blocks here is an iteration. Iteration 1. Okay. I have a bunch of RDDs that I build in there. Some of them are temporary results. The only thing that I need to cache are things that cross these boundaries, right? This internal one doesn't help me to cache them. They're only referred to in here. And if I cache this one, like right here, then I never have to go back and compute these. If I don't, so this is the thing though. If I don't cache anything, and I have, for example, a collect in here, or some sort of fetch a result, you know, I fetch a result back to the driver here. It does this tree of computation and produces a result, right? The next iteration, I do it again. You know, I'm using an accumulator, I'm using a for each or something like that. If I don't put any caching in, this iteration, it does this chain of computation, produces a result. This one does this chain of computation and also this chain of computation and produces a result. When I get to this one, same thing. It's going to compute all of this, all of this, all of this, and it'll compute in this order. But because of how RDDs work, right, they're lazily evaluated, and it's just it's the data flow graph. You know, I've got objects that I compute other objects from. So when I ask for a value, just trace up my parents, do the computation, all the way back. And if I have an expensive load operation before all of this, it'll happily reload the file each iteration. Okay? So, where to cache? Draw this out for your iterations. Say, okay, this RDD and this RDD are combined here by a join. This RDD is a map values. This RDD gets passed. And then say, well, if I break, you know, if I cache this right here, and each of these are just basically, this one is not, you know, it's just, it doesn't modify. And so it's effectively cached all the way through after that first load. And then this, and right here, if I cache here and here, or if I cache this RDD inside this iteration, then at this point, this is cached, and so basically no computation has to cross this iteration boundary. Is that clear? I don't see like clarity necessarily in the faces. Right, the same thing here. If this is cached, if it's just being passed along or something like that, or if I do cache there, if I cache the RDDs between iterations, then computation won't cross that boundary. Usually, you do have to be aware, especially if you're starting to start up 20 or so nodes, one of them might die, right? And in that case, it has its history. So if the cache goes away, if part of the cache goes away, it can go back and find the previous result, and it might have to go back. But in general, it won't, all right? Does everyone understand this sort of rule of thumb? Draw out your chain of computation, figure out where you can cut it and put a cache. No, unfortunately. So you can't delete, right, that I found. You know, there may be a deeper way, but in general, no. The reason you can't delete it is or effectively you can't delete it, is, so if you're worried about running out of memory, what should happen is as you cache new things, old things should just drop out of the cache, right? They may not be available. Cache means I'll keep it around while I can. If I can't, then I might have to recompute it. And that's why it doesn't actually go away. You can't necessarily say, get rid of these, because if a node goes down and part of this RDD is missing because a node has died, and I need to recompute it from elsewhere, I need its history, right? I need to go back through the chain, recompute that piece, which may involve a fair amount, unfortunately, and then rebuild that RDD from its history. So those still exist. But in general, you shouldn't need to. It should be like an LRU cache or something. I use it, and then it goes away. Sorry.
Yeah, it's an LRU cache, and there's unpersist. There's an RDD that unpersist.
Oh, okay, so you can. But you don't generally need to, that I haven't had to. So you can unpersist it.
So in this example here, what was the best caching scheme? Like you want to cache before all the iterations, so you're not caching
So you want to
cache in between each iteration?
You cache in between. So let's just talk about in BFS, right? You've got the node, that you build some neighbor structure, right? So that you have the graph. You have a graph representation. That's built by loading a file and then pre-processing, right? You don't want to do that each iteration. So you cache that, but it's static, right? The graph structure doesn't generally change, or shouldn't. So cache it then, after it's built. And then after that, you don't need to use it. That could be like this one, right? It's just being passed along. It's cached, loaded it once, built it. Distances, right? As you're propagating this information around, you're going to build some temporary RDDs and do some shifting around and maybe a repartition, get an output. At the end of the iteration, that becomes your input to the next, right? That new set of distances becomes the input to the next iteration. Cache it then. It's done. You don't want computation to go back through the other loops, so cache it. Because that's the only part, really. There might be other parts depending on your implementation, but if that's the only RDD that is used in the next iteration, it's the only data from the previous iteration used by the next iteration. If you cache it there, you won't have any of this lazy evaluation flowing through it into the previous iteration. Make sense? I just do RDD cache, yeah. That's just keep it in memory. There are a bunch of different things, but you only have to get into that if you've got huge RDDs that you can't keep in memory, or.
So that cache doesn't like do anything with the CPU cache.
No, yeah, these are separate. Cache is just yeah. Cache is basically try to keep this in memory. So cache just means a place where I keep stuff that that is faster than the place where it's in this case. It means the same as a CPU cache. It's like, instead of having to go to memory, I go to L1 cache. Instead of going to disk, or instead of going through the computational tree, I go to my cache.
This is going back one thing. Does filter maintain partitions?
Yes, filter does. Because it's basically anything that doesn't involve changing the key and doesn't involve a shuffle, right? Yeah, filters certainly could do this. You could end up, filtering everything that's only down to one partition. You could end up very imbalanced. So. If you call persist, so persist so there are several choices for persist. You can look them up online. In general, caching, and the problems we're working with, where you've got multiple nodes, even the Wikipedia graph, then it can sit in memory. And so you can just do this, and it will keep it in memory. I mean, it'll spill to disk if it needs to, but you can force it to be, persist this in disk so that you don't have to recompute it, but I'm not going to need it in a long time, or I don't want you to dedicate memory to it. No, not generally. I mean, if you do have a branch tree, like I've got my input, and I do some expensive computation and build an RDD, so it maybe looks like this. I've got some input, and I do something expensive right here, right? And then I branch and produce this RDD and this RDD, and then bring them back together, right? it should be smart enough to note that it doesn't, if there's a shuffle in here, then it might go back and recompute this. Like how it decides whether or not it needs to reuse this or can reuse this depends a little bit on Spark's analysis of it. And I'm not sure, I think if there's a shuffle in here somewhere, that's when it decides it needs to, or loses information about what's recently available. So in this case, or if you have, something, a long chain particularly, right, that's then going to come back at some point, this would be a good place to cache because you're going to reuse this result several times. And you want to make sure it's not done multiple. You might then use the unpersist in this case because this is something that doesn't straddle boundaries. So after you're done with these, may make sense. So I don't understand how unpersist and lazy evaluation work together. So in general, I haven't found much of a need to do this, though. It feels like most of the time, if you avoid shuffles, which we generally want to do, that if it splits data and then it comes back like this, it seems to do the right thing. So that it does result in a serialization. I mean, it can result in increased serialization overhead and things like this that may not be necessary. Certainly, if you just start sprinkling caches in there where they're not used, all you're doing is poisoning your cache. There's this term, poisoning your cache, which is sticking too many useless things in your cache, and then the things you do actually want in there are not there because you've ejected them to a slower storage level. No, if you just say .cache, it returns a new RDD, right? Yeah. So you call RDD.cache, it returns a new RDD, but when you evaluate things based on, when the actual computation hits that RDD, if it's already been computed, it just pulls it from cache if it's there. So you don't have to force a computation or anything. You just basically say, okay, this is a cached RDD. Think of it as a null operator that then makes it not compute again. Like you need to do that the other. Yeah. So just at the end of your RD, so you've got like do this, and then just say RDD2 equals RDD1 blah 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 cache. However, I am more of a fan of I've seen a lot of code that's like that's leveraging the sort of object-oriented behavior of RDDs, where you just go map dot flat map dot values dot cache dot this, and I much prefer just give them names, right? Break every time you create a new RDD, even if it's intermediate, almost always I just give it a name. I call it a variable. For one thing, it's the Spark UI will tell you where, if you've got an RDD in there, it knows which line that was created on and will tell you in the interface. So if you see a problem with a particular RDD, you know exactly which step it is. It's easier to pull out. And for another thing, it's just, my own worst enemy as a coder is me from a few days ago, right? I'm just like, dude, what are you trying to do to me? The more I type, basically long variable names are love notes to future me. You are the best. So I type, that's all my variables are named that. So it's not really that helpful. I'm like, dude, just, no, but if I write a long expressive, if I give long expressive variable names, when I read it in the future in a few days when I've forgotten everything, I can say, oh, this is what I was trying to do. So I much prefer that to the chaining thing. I mean, it's, I feel like super hacker when I'm like, blah, 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 blah. But in the future, I'm gonna be like, you're not a super hacker, you're just an idiot. All right. Oh, more questions, sorry. If I'm joining two RDDs and I cache them, if I don't cache them. Yep. Yes, that join will repeat. If you use that, if you do some computation and then if I do an action, right, and I get a value out of that join, and then I do some, do a map and then get a value out of that, it quite likely will recompute that join. You want to cache, you want to look at not necessarily just after a join, you want to draw out your computation. Figure out where lazy evaluation, where it splits, or where it splits basically, and hits either an output to you or the next iteration, where if I cut it off, or where is there duplicate computation that I can cut off with a cache, right? So if I trace back from the output function, right, and I hit, or I have, I trace back previous iteration and the output function, and I see that they both go through a long chain of computations, but there's no cache where they merged, coming backwards. That was a good place probably to cache, because then the output function will force it to compute, and the next iteration will be ready for it. Okay? Does that answer it? It's not necessarily just joins. It's anytime you have a split in sort of the computational tree, including iterations, where I could cause a recompute because of lazy evaluation, basically. Where it would be nice to say, okay, right here, I know compute is going to come through here twice, or my results come through this and go in two different directions, one to me, one to the next iteration. If I cache that, I only have to evaluate it for one of these. Okay. Yeah. It depends what sort of computation is below that. So this one, it may be useful to cache, but if you have a join and then just a couple of maps and then something that doesn't involve a shuffle, it'll probably it's not going to recompute because all the stage will be done at the same time. So basically, if the computation is bracketed by shuffles and there's no shuffle in the middle, you probably don't need to cache. If you do have a shuffle, then the stages might separate, or the computation might, right? Because it's going to do a stage and then it's going to shuffle and then do a bunch of other work. And that computation might need to go back. It might go back. So in general, try it. Sorry. I think it depends how much computation you're doing right after the join before they come back together or before you go on to the next one. So whether you cache right at that join or cache some later result off of that, it's case-based. So I can't give you a good answer that applies in all those cases. Okay. Yeah. Yes. Yeah. Subtract by key. Does it require shuffling? Yes. It's a pair. And so what it has to do is take the keys it's going to subtract and get them to, right? You've got things ordered by key on one side, and you need to get the keys you're going to pull out to the correct partition on that side that you're going to subtract from.
But doesn't it create a new one that's all of the first one minus the second?
Right, but it has to subtract off so subtract by key, you've got an RDD, you've got a smaller RDD that you want to take all the keys that are in the smaller RDD out of the larger RDD, right? That does require a shuffle because to take those out, right, they're split across workers in the distributed data set. I need to take the keys from the smaller one and get them to their partition where they need to be taken out. So if this one is not, right, if this one's not partitioned yet, I have to shuffle the smaller one into the same partitioning as the larger one. I don't know if it does the right thing in terms of, will it go only to the partitioning of the larger one? It could result in, okay, I'm going to shuffle them both together and then take the keys out. And so it could involve shuffling the larger one. So just make, any pair RDD, make sure it's co-partitioned beforehand. They're going to be co-partitioned. If they are, then it's not a shuffle. Yeah, then it's more like join, but minus join instead of plus, you know.
I was doing joins, just like one join operation, but in a loop, and like grab, join, queue, and then I just for kicks, I switched it to queue, join, grab. That should be the same.
I feel like it's the same. Looking at it, I was trying to figure this out, whether joins you want to do big, join small, or small, join big. They seem to be the same.
So one operation did the same thing, but in a loop, it
In a loop, I think then I didn't try chaining them together, so I don't know what will happen there. But it seemed to do it right.
So two RDDs are not co-partitioned, and you use some operation on that, would that cost more than repartitioning them so that they're co-partitioned before doing the operation?
No,
Isn't that shuffle exactly equivalent to the?
no, it shouldn't. And that's why I suggest always making sure it's co-partitioned before. Because then you have more control. It's more explicit. You say, I have this many partitions and I want that many. In some cases, you may be, if you're doing a one-time, right, you've got two RDDs and you're going to join them and then you're just going to use that data and you don't care, you know, how many partitions they have beforehand, and you're only going to do this join once. You're not trying to preserve any structure or anything like that. Then the code is simpler if you just join them and go, right? So there's no, and that's the case, the one case where I'd be like, I don't really care. I'm just going to join these and process further. Before that, it may be worth it, particularly if you know that you want a certain partitioning structure afterwards in terms of the number of partitions. All right.
I think this is really basic, but I forgot, like, the things that make all the lazy actions happen immediately are things like take, collect, and
Take.
also all the joins and stuff.
No, joins don't. No, not joins.
So, like, in that example where you have all those, like, you know, that intermediate nodes, if you don't have anything that takes action,
Then,
like that,
then nothing will happen. But at some point, let's say I do take an action here, right? You know, take. So it'll force this computation. Then there's a question. If I've got all of this, and I've got an expensive operation right here, right? This is the expensive operation. How many times is this going to happen?
Would it happen only once? Because
One would hope, but if there are others, you know, there might be some other shuffles or something over here on this chain of computation that might keep this from being available, right? It's going to break into stages and do the computation back in the, you know, it's going to break it into stages separated by shuffles. There's some question whether this, you know, right? It's going to do this expensive operation at least once. The question is, when I get to produce this RDD and when I, you know, when I produce this, this, and this, is that output still going to be available? Maybe, probably. But I know it's available if I cache, or I know that it won't cross that boundary more than once. So it's more just, if it's going to be available, then I was going to cache it anyway, right? Implicitly. So why don't I make it explicit, and then I don't need to worry. Then I don't need to understand what Spark's going to do in terms of scheduling and storage and stuff like that. I can say, store this. Please don't compute it more than once.
We already went over this, but what's a good rule of thumb for partitioning? Is it based on your data?
Based partly on your data, in general, you want it to be roughly, basically 4 times the number of cores that you're running on. So we have a certain number of machines in our cluster. Each of them has 4 cores. So when we launch, that was in this slide. When we launch the Spark submit, we'll tell how many executors we have, which is basically the number of machines in our cluster. We'll say each of them has 4 cores. I've been lying to it and saying 8 because then it launches just so that that turns into how many Python processes are running underneath. So if it's IO bound, more doesn't hurt, but 4 is safe. And then I say, okay, well, if I've got a, you know, for example, I launched a 5-node cluster, so I have 4 workers. I'm going to launch 4 4 cores. So I have 16 Python processes underneath, basically. So now I have 16 workers. I'm gonna make sure in partition probably about 64 to 128, somewhere in there. I think actually for the Wikipedia I bumped it up to 256 just to make them all small.
And you keep that consistent throughout your.
So we're about to, yep. Then the next thing is I'm gonna partition it this, and I'm gonna guarantee that everything is partitioned like this for the rest of my life. Okay? More questions? I think this will show some of that in action, hopefully. All right? Looking at big blocks of code, I know it's not fun. This is also on GitHub if you just want to look at it there. This is just the PageRank algorithm. PageRank algorithm, we have like 15 minutes. I'm going to try to get through some of this. I'm happy to stay a little bit later if people want to. PageRank algorithm is basically this. I'm a random surfer. I go to pages, I randomly choose a link, and I click on it, and I click on it, and I click on it. Sometimes I choose another random page. PageRank is what pages do I spend the most time on, and those must be the most important because everyone knows random surfers are the best surfers. All right, that's all the PageRank algorithm does. It has two probabilities. One is jump to another page. One is stay on the page but jump to another page it links to. Okay, that's all it does. It's a Markov chain process, and then the PageRank algorithm is just trying to compute the steady state of that Markov chain. The top of this should look fairly familiar to you, right? Start up, particularly on AWS, make Spark be quiet, please. Even so, you get like at least a page of output before it even gets to that line, all right? And I load the two text files. And I'm just going to split them into 32 to make some reasonable number, right? I don't know what it would actually choose here. I could make that smaller, but don't put it all in just two partitions, please. So 32, 32, that number is not important, okay, just as long as it's large enough. All right? Now I've got my data in. Now I'm going to start doing some computation. The first thing is I'm going to process the links into a neighbor graph, all right? This lecture is not so critical about that, but I'll show it just for completion. So I'm talking about this call right here, okay? Because it's in a text file, so this is what I do. It's right here. That doesn't help you see it, probably, all right? It's got remember it's structured as integer, colon, integer, space, integer, space, integer, space, integer. So I split it first at the colon space, and then I split each of the other ones by things, and I convert them all to integers just for simplicity, okay? All right, instead of strings, I have to do this explicitly. So now I've got my neighbor graph. It's the adjacency list representation for a directed graph. I've got a node and a list of nodes that it points to, okay? Any questions so far about this? All right, back to main.
Is Spark become better with long, like, pairs, or just like wider?
I don't think it actually. So there's more overhead in the long. So the other representation you could do here is you could blow this apart with flat map, right? Where every edge is basically the edge structure, right? So I have every edge is A to B, A to C. There are costs and benefits to each one. That one costs more because that source node is represented multiple times.
I couldn't deal with the list, but then you have to collect and
You don't have to collect, but it is trickier. I mean, you have to do more flat map things where you take a list of things and put them into a structure of a thing. It's fine. Either representation is fine. You're going to get a little bit more overhead, but your code might be simpler, and some of the structures may be easier. But I don't think it matters too much. I don't think Spark has a preferred representation. Okay, back to main. All right. Does everyone understand the representation of the graph here? Should be familiar. Most of you, I think, chose that representation. It's not, as I said, it's not critical. So now I've just got an RDD. First, the key is a node, and the value is a list of nodes it points to, as detailed in this comment right here. All right. I'm going to create another RDD just for looking up names. All right. I've got this long list of names. So I zip it with an index. When you zip with an index, it takes the first column and adds 0 through whatever as the right column. So I just quickly map that, takes in a name and an ID, and switches it to ID plus 1 because this data is plus 1 is one index and the name. Then I can look things up. And I sort by key and cache that. Sort by key so that lookups are fast. Cache because I'm going to use it multiple times, okay? I'm not going to use this in my actual computation. This is just the names. But I'm going to cache that because I'm going to do multiple lookups at some point. This would matter more if I were detailing paths like in the BFS algorithm, okay? All right, we got our data now. It's all loaded, it's pre-processed. Questions about those steps so far?
Why would you partition by that? You're going to use it again and worry about partitioning? Just to understand the logic behind it.
You mean page names?
Yeah.
I'm going to set up partitioning for the computation in a second. The page names, if I sort by key, so you get fast lookups from hash partitions or from sort partitions. Sorting also makes it fast. It makes it basically as fast. So this one, it's 6s. There was a bug that I encountered in the Shakespeare stuff with lookups of tuple keys, and so I've been a little bit wary. But it's in the homework. A few people have come up to me and said, "Oh, I know, look in the homework," and it's like, "Oh yeah, okay, sorry." Yes. No, the titles list is just a list of titles. So you need to do this. But zip with index lets you get that index pretty fast, okay? That's also useful for problem 6, zip with index, if you haven't gotten to it yet, for getting things in order because you need the number of the words. All right, are we good with the pre-processing step? I cache page names because I don't want to load it again. I don't want to pre-process again. I just want to use it, okay? That's important. All right, now we're going to set up partitioning. All right, and from now on, my entire world is partitioned. I have roughly 16 workers because I did, in this case, 4 by 4. 4 workers, 4 cores each. I'm going to use 256. That's about 16 partitions per worker. When I say, rule of thumb, 2 to 4, the noise is in the exponent, right? 4 partitions for every worker, 16. Don't go to 100, but anything that's got, between 1 and, is probably below 50, it's fine, right? I'm just going to do this because it produces a reasonable number and it works, all right? Take the neighbor graph. I'm going to replace it because I live in partition space. I'm going to partition it by 256 and I'm going to cache it, okay? Because I'm going to be referring to this neighbor graph over and over. And it is static, and this is where I compute it, and it's partitioned this much, and I don't want to touch it again, okay? Are both those points clear? I've computed it. I'm going to partition it by this much. This is going to be my chosen golden partition number. Don't touch it again, all right? And this number and this partitioning is going to influence and decide the rest of my computation.
You didn't say that it should be a prime number?
No, let's forget about prime numbers and caches for now.
Okay.
That's more when you start getting to memory caches, where like associativity starts to matter. This one, I could use 257, it's fine. At that point, it's going to be noise, but this way, it's very balanced.
And where can you find the flag?
Find the what?
What you're showing right
My code, it's in my GitHub, so just search for my first name on GitHub and look at my most recent repository. All right, so I'm going to do a little bit here. I'm still going to use Kevin Bacon and Harvard University. I'm just going to find the nodes using the lookup the lookup function. I have to use it in the reverse because my lookup function, right, is now from node number to name. I want to know the node number that it has. So I do that by filtering out all the nodes named Kevin Bacon and collecting them. This is not in my loop. It's fine to collect here. I should only get one back. There should only be one Kevin Bacon. And then I'm going to pull out the node ID, which I get one element back from collect. From filter, it should become an RDD with one element. Collect gives me a list. I pull out the first element of the list. I pull out the ID, the first part of the tuple. And I do the same for Harvard University. Okay? I just want those 2 nodes because I'm going to print out some values for them.
That assert, if it's not true, do you get like a null value?
No, if you assert something that's false, if you assert and it evaluates to false, crash. It's very useful. Like assert is give up. If you want, you can also put like a comma and a reason there, and it'll print out the reason if you want something more clear. Otherwise, it just prints out the line of code. So that's just a script. I'm going to have some more asserts in here. It's basically, I think the code does this. If it doesn't do this, then I'm wrong and stop running because I'm an idiot, right? So
Why did you flip around the ID and the name?
So later on, I'm going to want to, so I need to look things up more by node number, right? Because all the links, the neighbor graph is all node number links to node number. So in general, what I'm going to be doing is looking for, I've got some node and I want to print out something about it. In this case, I want to print something out about certain nodes. So this is more from BFS code, the BFS code which I wrote before and extracted this from. But in general, don't look up the node index for, like you'll do this limited number of times. You'll find a few nodes usually. if I wanted both a two-way, if I wanted a two-way lookup, then I would build another RDD keyed the other way, right? And I could have done that. I would still need to use zip with index and all that stuff because I still need the number. But is that clear? Okay. All right. I have a couple of nodes. I'm going to watch those nodes in my PageRank loop. I've got my neighbor graph, right? I'm ready to go. So scrolling down, and call PageRank, all right? I'm going to pass in the neighbor graph, and then a certain number of iterations. I'm going to give it the page names and tell it to watch these two nodes while it goes. All right. PageRank. Two constants to control its behavior, right? On this random clicker. Jump fraction is click fraction is the percent of the time that I'm just going to stay on a page and click some random link. And then jump fraction is I'm bored with this page. You know, I don't like these cat pictures. I want better cat pictures. I go to Google, I search up new cat pictures, and jump to a new page and start clicking around the cat. Okay. These are sort of the defaults that they put in their original paper when Google. All right. About 85% of the time, stay on the page or click on a new link. The rest of the time, just jump to somewhere random. Okay. They should sum to 1 because they're probabilities. Other than that, not important. But to explain the algorithm here, what we're doing, that's what's going on. And then what we do is we just have basically an infinite number of clickers that start out to spread throughout the entire web, the entire graph. So we set all the nodes equal to 1 initially. Yeah, or if you read the original paper, it's actually they make it a probability and they divide it by all the nodes and set it to 1 over n, but it's just a scaling factor. It doesn't actually affect it. All right, so that's what I do here. So sometimes it's 1 over number of pages. I'm just going to do this. All right. I'm going to set my page ranks. This is the values I'm going to compute. I do map values. Map values preserves partitioning. And I want it to be, I have a graph that's node links to neighbors. I want this to be nodes value. So I ignore the neighbor list. This is just like, underscore is a variable name in Python. It's used for a variable I don't care about. And I'm just going to set it all to 1.0. Does this line make sense, what I did here? I'm not setting. I can't set. It's an RDD. I can only, so this is, I had an RDD that was nodes and neighbors of nodes. And I'm mapping that to nodes and 1. It's a new RDD, but has the same partitioning. So, because it's map values, not map. So I can assert this, that they're co-partitioned, okay? And I do assert this and I check it. This costs nothing in my compute. It's, well, more or less. It's run on the driver. It's run even before the lazy computation launches. Basically says, I've got an RDD. Does it have the same partitioning function and the same number of partitions as this other RDD, okay? Yep. It could have been an expression of what, though? Yeah, so then in that case, I would have put V here. So map values takes a key value RDD and just passes V to the function, the lambda, or whatever I call it. And you can do something with that V and return a new value, and that becomes the new V in the new RDD. In this case, I don't care what's in there. I'm going to put 1, okay? We have like 5 minutes left, less than 5 minutes left. I can either keep going through this code, or I can launch. Actually, I'll let you guys launch it on. If you run it on AWS, I'll send out the commands. You can see how this works. It takes, you know, on the default setup, about a minute an iteration. So I think the code is probably more useful. Okay.
Is there a way to like take chunks of this data set and test everything locally?
Yes. So if you want to take a smaller chunk of the data set and test locally, we can probably build that data set. But if you want to just run it on AWS on a smaller data set, filter your links at the beginning and only keep like the first 10,000. Right. We can probably build that. You can just run it on the Marvel graph too, though. On the Marvel. graph too. This is small. All right. All right, so we've got the initial page ranks. We've got the neighbor graph. All right, this is important. Neighbors and page ranks are co-partitioned, and we want this always to be true. So the rest of the stuff's going to be building that. All right, and then we do this loop. Beginning of the loop, I want this to be, that statement to be true right at the top. So I'm going to make sure it's true. Better be true. All right? There's no okay, next thing. I've got neighbors and I've got ranks, and I need to figure out if I'm on a page and I randomly click on the page, basically I need to take my current rank and I hand it off to all my neighbors. Okay, that's this, the next few steps here. First thing to do then is to get the ranks and the neighbor pages in the same space, and that's to join, right? So this neighbor join ranks is neighbors join the page ranks. No shuffle there, right? Because it's co-partitioned, okay? There might be, yes? Then the partition, maybe you had a map in between. If you see that, and actually, I should have something else right here. I can spell cert. I can make Emacs spell it for me. If that happens, then Spark has lost its knowledge of the partitioning, possibly due to a map or something else. We can look at this, but it should have the same number, right? So there shouldn't be a shuffle here, and I should have this result. And then, so now I've got this structure, right? I've got the neighbor list and the node rank from that node across all of them. All right, it is time. Who is interested in continuing anyway? Who has to rush off? All right, if you have to go, go ahead. I will, so you can read through this online. If you send me questions about specific things, I'll try to answer that. I've tried to document it as well as very well, so that it's readable that goes through. If people want to hang out, I don't think there's anyone in this room, so I'll just continue for now. But I'll excuse whoever needs to take off.